All right, so good afternoon, everyone. We'll start with our workshop 12 material. We're looking at electrophilic aromatic substitutions. And we're looking at activation and deactivating benzene, right? We're thinking about halogenation specifically. And what we're going to do today is just think about reactivities and kind of ranking them, which groups would be better for electrophilic aromatic substitutions, which functional groups would be worse. Excuse me. Yeah. So we'll start off with just looking at, in example one, we'll look at two different compounds, right? Two different molecules. The first is phenol, right? And in our phenol molecule, we can consider this to be an electron donating group. And in our second molecule, we have our NO2 or nitro group, and we can consider that to be an electron withdrawing group, right? So for our electron donating group, if we were to think about resonance structures that we can draw, our oxygen should get lone pairs. We can push electrons and generate a new carbon-oxygen bond. And this allows us to, if we've taken electrons from an atom, we need to add electrons to an atom. So this actually allows us to add aromaticity to add electron density to our aromatic ring, right? So now we have a double bond to oxygen. Oxygen now has a positive formal charge, and now we have a negative formal charge on a carbon in our ring, right? That would be one resonance form. And you can imagine that we can push these electrons to other carbons in our molecule, right? So when we consider other resonance forms for this molecule, we can put our negative formal charge in this position there, right? And now our double bonds will be present here and here. And then you can imagine that we can do this one more time. And in another resonance form, now our negative formal charge is present on the left, right? At the top left, our double bonds are present there. So these would all be resonance forms for our electron donating group. And then lastly, you can imagine that we can regenerate our species, right? We can get back to our first structure of our phenol. If we push electrons back to generate the double bond, our aromatic ring, and then give oxygen a lone pair of electrons. Okay, so we can do that, and that would be our electron donating resonance forms, right? And for our electron donating resonance forms, you'll notice that we have, remember that we're talking about electrophilic aromatic substitution. And if we want our electrophile, right, which has a positive charge, so we're going to think of our electrophile as E+. If we want our positively charged species to form a new bond with our aromatic ring, then we want to look at sites or locations on our aromatic ring that are negative. So you'll notice that for electron donating groups that are ortho and para positions, right? So the ortho position is next to the substituent, orthogonal, right? Ortho is next to, and we'll just say this is our substituent of interest, and our para position is directly across from or 180 degrees, right? So the para position is parallel to our substituent of interest. So this would be our electrophilic aromatic substitution. If we look at an electron donating group, we see that because we have a negative charge at both our ortho and para positions, then our electron donating groups are generally better we can have better nucleophiles added at the ortho and para position for if we have an electron donating group present in our molecule. So what if we have a different type of molecule where instead of having an OH, right, we see our oxygen has lone pairs, which can add electron density to our ring. What if we have an atom with a positive formal charge, or an atom that can take electron density? Then that means that we can take electron density away from our ring, and we'll consider this to be an electron withdrawing group. I'll abbreviate that as EWG. And what we're saying now is that we can push electrons to form a new bond between our substituent and our ring, and the carbon in our ring. And then there will often be other atoms electronegative atoms like oxygen that can take electron density and stabilize the charge, right? So now if we think about the other resonance form for this, so now our nitrogen has a double bond, right? One oxygen should have a negative formal, both oxygens should have negative formal charges now. Our nitrogen has a positive formal charge, and now we can see that from electron pushing, we should have a positive charge at the ortho position. And if we continue to push electrons, you can imagine that if we want to eliminate the positive charge, or sorry, shift the positive charge, now we'll have a positive charge at our, so this is NO, NO, negative and negative. Now we have a positive formal charge at the para position, and then in our last resonance form, we'll get a positive formal charge in the other ortho position. So now our double bonds are there, and we push electrons here and here, sorry, here, and so we push electrons here, and this allows us to put a positive formal charge there, so nitrogen with an oxygen, and the oxygen a negative formal charge, right? So these would be the resonance form for our electron withdrawing group, and you can see that now we have positively charged carbons at our para and ortho positions, right? So that means that positions that are not positively charged would be better for our electrophilic aromatic substitution. So those positions will be our meta positions, and they'll be located here and here on all of our molecules, right? So those are the positions meta, right? So they're basically, if this is our carbon of interest, where our substituent is, our meta position is 2 carbons away. Our ortho position is 1 carbon away, and then our para position is 1, 2, 3 carbons away, right? So we'll have better nucleophiles. If we have an electron withdrawing group, our nucleophilic attack will generally occur at our meta position. So that's kind of how we will think about looking at electron donating and electron withdrawing groups. And we can classify different substituents based off of their directing ability. So we can think of things as being ortho-power directors or meta-directors, and that's whether they are electron donating or electron withdrawing. So when we have an ortho-power director, we're going to say that our substituent, the attachment to our ring, is activating, right? So these are activating the ring, and we can think of activating the ring as adding electron density to our ring. If we have an electron withdrawing group, we can think of these as deactivating our ring. So these are deactivating, and they are called deactivators, right? So if we want to think about a list of different activators and deactivators, then some ortho-power directors, right, for our electron donating activating species. If we want something that's strongly activating, so I'll just write SA. A few examples of strongly activating substituents include our amine, NH2, right? Another strongly activating species, or all of our amines, we can write it as NHR, NR2, right? All of those amines would be strongly activating. And then also other elements with electronegative atoms like our OH group or just an O minus, right? Those are all strongly activating species. We can have moderately activating species, right? So those are strongly activating. If you want to think about moderately activating species, so we'll write that as moderately activating. Our moderately activating species now have longer or larger structures. So now instead of just having protons or a large number of protons directly attached to our electronegative atom, we'll make our carbon chain a bit longer next to our electronegative atom. So examples of that can be our amide, where we have NH, and then we have COCH3, sorry, C, double bond O. I don't know what I just did. C, double bond O, CH3, right? So if we have an amide, and whether that amide is just a methyl, or if we change this up to an R group, a larger R group of some sort, we can include our amides as moderately activating. We can include our methoxides, so OR, and that includes OCH3. Those will be examples of moderately activating species, right? So those are our moderate activators. And then lastly, if we want to think about our weak activators, then we'll just think of our alkyl species. So for our weak activators, which I'll just abbreviate as WA, now we can just think of alkyl species like CH3, really any alkyl group R. We can think of our C6H5, our aromatic ring. All of those can be considered to be weak activators, right? So those would be our weak activators. And these will all direct in the ortho and para direction. So if we're adding a new substituent, so if any of these substituents are already on our aromatic ring, and we're adding a new substituent, that new substituent will either be in the ortho or para direction, like we saw in example 1A, right? Another strange class of species that are ortho-para directors actually are deactivators. So we have weak deactivators that can be ortho-para directors, and these are our halides. So these include fluorine, chlorine, bromine, iodine. So these are kind of a special class of activators. So I'm going to put these in blue. Right, so this is a special class of ortho-para directors, but they are deactivating. So these are still ortho-para directors, right? So everything we have so far are ortho-para directors. And these are different because they're deactivating. And that just means that because of their electronegativity, they have a slightly different reactivity, or they have the reactivity we see in B, but they are still ortho-para directors because of the electronegative atom present, right? So those are our ortho-para directors. For our meta-directors, right? So if we're looking at B now, and we're looking at our meta-directors, then we want our deactivating groups. So we can have moderate or strong deactivating groups. And if we think of our strong deactivators, then that list includes NO2, right? We can have NR3+, our ammonium species. We can have any halogenated species, so CF3, CCl3. So our halogenated species are all strong deactivators. We can have moderate deactivators. So these will be our strong deactivators. We can have moderate deactivators. And for our moderate deactivators, we're thinking about our cyanide ligand, right, our CN. We can have our SO3H, our sulfonyl group, our carboxylic acid, CO2H. We can think of it also being CO2R, right, where we're generating an ester. We can think of aldehydes as CHO as a functional group, or ester COR, or sorry, ether COR. So those would all be our moderately activating groups. So those would be moderately deactivating functional groups, and all of those would be meta-directing, right? So these are our meta-directors. And then for our activating group, these are our ortho-para directors. So all of these will be our ortho-para directors.